Okay, folks, hope you're all doing well, and we'll try and get started into our next unit here. We've made our way through organic chemistry. What we're going to get into next is a little bit of a math unit, so don't get afraid already. It's fairly straightforward from the math point of view, and the challenge will be just learning the chemistry so you can understand what to do with the math. Okay, so the math is actually fairly simple here. But we just have to get some understanding of what we're measuring and what we're trying to calculate from a chemistry point of view. So we're going to take a look at two things, these balanced chemical equations. So we've used balanced chemical equations in the past, and they tell us kind of what is reacting. So C2H2, which is ethene or acetylene, and O2, which is oxygen. We want to start making use of these numbers, the 2 and the 5, so that we can start to talk about, well, how much oxygen. Well, we know that 2 molecules of acetylene react with 5 molecules of oxygen, but I can't really measure out molecules. So it would be very helpful if I could know a mass of oxygen, or better yet, maybe a volume of oxygen. Since it's a gas, it's easier to measure it in volumes. A volume and mass of these two things. And so then I could go to the lab bench and I could measure out the volume and mass that I need, and to make sure that I put together the correct amounts so that this reaction happens most efficiently. If you remember when we talked about a little bit about combustion a couple weeks ago, if I don't have these two things in the right combination, a 2 to 5 combination by volume, then I don't get complete combustion like I have here. I'll end up with making things like soot, and I'll make things like CO, which is carbon monoxide, and I make a lot less of this. I make a lot less energy. So a lot less energy gets made if I don't burn things completely. So in a reaction, I can use these this balanced chemical equation to decide how much of gas versus oxygen do I need to mix, so that I make sure the mix is proper and gives me the best combustion as possible with the least amount of kind of harmful waste products being made. Okay, so that's just one possibility of where we could use it, but it's going to be so we can calculate out what's going on in a reaction and how much we should start with, and finally, what should we expect to see as our yields? What can we maybe make on at the end of a reaction? Okay, so that's kind of our long-term goal. To get started, we're just to make a little bit of a difference from what we have been doing. We've been doing qualitative analysis, looking at colors and what it's doing just by visually seeing things. This is we're getting into now is another aspect of chemistry called quantitative analysis. So it's a way of actually putting a number and measuring certain things as we do the chemistry. Okay. For instance, when you go to the doctor, they might give you a little test, and there's those little test strips, and you can they dip it in your urine, and then the strip changes different colors depending on what's present in your urine. Okay, that's kind of a qualitative test. Say, for instance, if this line shows up, it shows that you have sugar in your urine, which is not a good thing. You don't want sugar in your urine. But it doesn't really tell you exactly how much. So quantitative tests would be more like if you're familiar with anyone who has diabetes, they have to prick their finger. They put a little bit of blood on the paper, and then they have a machine that reads it off and gives them a blood glucose number, like 0.6 milligrams per liter. Okay, that's quantitative. Tells you a lot more, gives you more details, and specifically says how much of something there is. So anytime that we have that, so we have in this case, a unit, how much, and then what we're measuring in this case, kilograms or milligrams per liter, whatever the unit is, we're talking quantitative analysis. Okay. Now, in particular, we want to be able to count, like here's a little drop of water, how many water molecules are actually in there. So that's what we want to learn how to do, is how to count those water molecules. And it's not possible. We can't see water molecules under a microscope. So it is impossible to just physically count them. But there are some relationships we can use that have been invented over time, and chemists have found ways of being able to count atoms without really counting them. So we can use other information to calculate how many atoms would be in a sample, and then we can do our math based on those calculations. Right? So that's what we want to get into, a way of counting atoms, molecules, electrons, particles, whatever we want to count. We want to look at a way of counting those particles and coming up with numbers of how many we have in the beaker. How many particles have we put on the scale? How many molecules of a product are we going to make? And so that's our job for the next little bit. So this comes in with a new unit, and this is the part that gets a little challenging because it's new for all of us. And we're going to learn how to measure something called the mole. So a mole is, I'm going to post this video and you can have a look at it. A mole is just a way of counting. If I was to ask you to count by dozens, most of you could count by dozens. Right? If I said, well, you have 36 donuts, well, then we know if we divide that by the number of dozen, what is in a dozen, which is 12, then we know we have 3 dozen. Okay? A mole is a lot like that. It's just the number that a mole means is not 12. A mole is a very large number. So a mole actually means 6.02 times 10 to the 23rd of whatever particles. You could have 6.2 times 10 to the 23rd donuts. That would be a heck of a lot of donuts. So that's 6. Let's just write this out. That's 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 particles. So that's what the 10 to the 23 means. It's called scientific notation. It's a 6 with 23 other numbers after it. So this is an incredibly big number. It's about what you'd find in maybe about 18 mils of water, about a tablespoon of water. You'd find that many water molecules. 6.2 times 10 to the 23rd, or 6 sextillion molecules of water would be in about 1 tablespoon of water. Okay? So that's why we're switching to this number. I don't want to be counting numbers like 6.02 times 10 to the 23rd. They're difficult to use. So if I have 6.02 times 10 to the 23rd particles, then I can just convert that. And I can say I have 1 mole of particles. So that's where the mole is going to come in handy. It's just a way of counting incredibly large numbers of particles and converting them into a number that's a little more manageable to think about. Right? If I had 3.01 times 10 to the 23rd, which would be about half this number, then I'd have half a mole. And if I had 12.04 times 10 to the 23rd, well, then I'd have 2 moles. So this number 6.02 times 10 to the 23rd, it's just like the 12 from a dozen. It lets me figure out how many moles I have. Now, if you watch the video, you'll know that that number is called Avogadro's number, simply named after him because his work was the first to introduce this idea of being able to count the particles of gas, count the number of molecules in a sample. Okay, so a dozen has 12. A mole has Avogadro's number worth of particles, which is 6.02 times 10 to the 23rd. Okay. So this is a number that was first suggested way back in 1811. So it was around for a long time. His work was somewhat ignored because we hadn't even come up with a coherent idea of what an atom was in 1811. So counting particles of gas was kind of a strange and new idea. But his work piled on with other people's work over the kind of successive 100 years kind of came to this number of 6.0 times 10 to the 23rd. And we just call it Avogadro's number in honor of him in terms of he was the person that started the work. And this number has been recalculated over time. You'll probably be able to find it published to more precision, more decimals. But for our work, 6.02 is precise enough. And that's the number that we'll be using for Avogadro's number as we go ahead. Now, just pulled up an idea, just to give an idea of what a mole looks like and how much we're really counting, because it's an incredible number of particles. But if you looked at, this is just a comparison using a green peas. And if you move anywhere from 100 would fill a teacup, and you can look through the rest of these. As you move down through it, we just continue to fill up more and more containers. So here's 1 trillion. A trillion would fill up a small home. Oh, sorry, all the homes in a small town. If you went to up to a mole, you could make 250 planets like Earth covered in 1 meter deep of peas. So you cover the whole planet 1 meter deep, and then do that 250 times, and that would be the number of peas in a mole of peas. So when we say we have a mole of water in about 18 mils, or a tablespoon of water, that's an incredible number of particles that are just in 1 tablespoon. And then spin that up into a swimming pool, a lake, an ocean, and you can imagine the number of molecules that we're talking about. Actually, it becomes almost too hard to imagine the number of particles. So we'll stop that here as our introduction to the idea of what a mole is. And in part B of this video, I will go through how we can start to calculate things like the number of moles, the number of particles. So we want to be able to begin figuring out how many molecules are in that beaker of water, how many atoms are in that piece of gold, how many atoms are in the balloon filled up with helium. So those are the kind of questions we're going to work on first. And I'll go through this formula, which you can see on your screen, show you some examples, and we'll take your questions after that. Okay. So for now, we'll say goodbye, and please check out part 2.